Welcome students, welcome to day 3 POC-II crash course. So thank you so much for joining. So as you are aware, in yesterday's session, I have discussed about reactions of benzene, that is aromatic electrophilic substitution reactions of benzene. So I hope yesterday's concept is crystal clear to you. And in today's live session, I'm going to discuss about effect of substituents on aromatic electrophilic substitution reactions of monosubstituted benzenes, which includes theory of orientation and reactivity in these particular reactions. So again, as you are aware, I am discussing only the examination point of view, important questions only. So this particular topic is also very, very important question. In fact, it is a definite question in your final examination. Stay with me till the end of this particular live session because I'll be showing you some of the most important question, that is model questions, how you usually get questions from this particular topic at the end of this particular live session. And I'll be also discussing how to write the answers for these questions, so that you can take a screenshot of these questions and prepare for the same for your final examinations. Coming to the quiz, students, at the end of this particular live session, quiz will be enabled and the details of the quiz, that means link for the quiz, will be provided in the description. So as soon as this particular session is completed, revise the topic once and then attempt that particular quiz. Coming to the previous 2 days quiz results, none of the students so far they got maximum marks in those 2 earlier days quiz. Okay, so as you are aware, the student whoever gets maximum score, I'll be giving an exclusive offer to become my community member. Now, what is this community and what is this offer? If you want more details, I have explained already in one of the earlier YouTube video. The link for that particular video I have already given in the description. So you can watch that so that you will come to know exactly about my community. So my community, as you are aware, it is Cam Superstars Hub. So what is this community and its details, you will come to know by watching that particular video. I hope you are ready with notebooks, pens and water bottle. So before we jump into today's session, please subscribe my channel if you have not yet done. If the concepts, whatever I am teaching, are useful to you, if they added any value to your learning, then please subscribe my channel. And also please refer my channel to your classmates or friends. Because usually how YouTube algorithm works, as you are aware, and that if the number of subscribers increases, then automatically YouTube algorithm pushes my channel to other students also, those who usually watch educational channels. Okay, so in that way, indirectly, you and me together, we will be helping some other students who are lacking the facilities or teachers guidance. Okay, so please help those students also. So your single subscription in that way indirectly helps many of the students, those who are really in need of such type of channels. Once again, thank you so much for joining this session. Now let's jump into today's topic. By this time, you might have understood the mechanism involved in aromatic electrophilic substitution reactions of benzene, because I have discussed this particular topic with 5 different examples: nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. Now in all these reactions, you might have observed one common thing. That is, in all these reactions, there will be formation of monosubstituted benzenes as the products: nitrobenzene, benzene sulfonic acid, chlorobenzene, alkyl benzene, and also ketone. So all these are the products which are obtained in various electrophilic substitution reactions of benzene. So all these are the examples for monosubstituted benzene. Now the question is, what type of reactions these monosubstituted benzene derivatives will undergo? Because the monosubstituted benzenes are also having structural similarity with benzene, and also the type of chemical bonding is also similar, they will also undergo similar type of reactions. That means even monosubstituted benzenes, they will undergo aromatic electrophilic substitution reactions. When we talk about reactions of monosubstituted benzenes, we usually get 2 types of questions. The first one is, what about the reactivity of these monosubstituted benzenes when compared with benzene? That means whether these monosubstituted benzenes are more reactive or benzene is more reactive towards electrophilic substitution reaction. The second important question is, when these monosubstituted benzenes are subjected for electrophilic substitution reaction, again there will be attack of electrophile. Now, what is the orientation or point of attack of the second incoming electrophile on the structure of monosubstituted benzene? Now, let us try to understand the answers for these 2 questions. So, these 2 questions are answered by 2 concepts. The first one is effect of substituents on aromatic electrophilic substitution reactions. And the second one is theory of orientation and reactivity in monosubstituted benzenes. So these concepts will be explained with the help of two cases. Under case 1, I'll be focusing on orientation. That means when monosubstituted benzene is subjected for electrophilic substitution reaction, what will be the preferred point of attack for the incoming electrophile when compared with unsubstituted benzene? And in case 2, I'll be mainly focusing on reactivity. That means what is the rate of reactivity in case of monosubstituted benzenes when compared with unsubstituted benzene. So each of these cases will be further explained with the help of two examples. So mainly sulfonation of benzene versus toluene and nitration of benzene versus nitrobenzene. These two examples will be discussed. Now let's get into the topic. In this, the first example is sulfonation of benzene versus toluene. You are well aware that whenever benzene is subjected for sulfonation by treating with 2 moles of concentrated sulfuric acid, it forms benzene sulfuric acid in 100% yield. Now, when the same sulfonation reaction is performed for toluene, so here toluene is a monosubstituted benzene. So when it is treated with 2 moles of sulfuric acid, the incoming sulfur trioxide electrophile, now it has got 3 chances. That is, it can attack at the 2 ortho positions. These are the 2 ortho positions. Okay, or it can attack at 2 meta positions. So these are the meta positions, or it can attack even at para position. So this 4th position, which is exactly opposite to that of methyl group on the benzene ring system, is the para position. So the next incoming sulfur trioxide electrophile can attack either at ortho position, meta position or para position. That means there is possibility for the formation of here 3 isomers of disubstituted products. Now let's see. So here this is the structure of ortho isomer. So we have just attached sulfonic acid moiety ortho to methyl group. Okay, so this is the structure of ortho isomer, and this is para isomer where sulfonic acid moiety is present at para position to the methyl group of benzene. And this is meta isomer where the sulfonic acid moiety is present meta to that of the methyl group on the benzene ring system. But when the resulting products were analyzed in this reaction, it was found that ortho isomer is formed in 32% yield, para isomer is formed in 62%, while meta isomer is formed in only 6%. Out of the 3 possible isomers, whenever methyl group is present on the benzene ring system, the next coming electrophile prefers to attack mostly at para position because we got this para isomer in 62% yield, and then after para attack, ortho attack is preferred because we got ortho isomer in 32% yield. This clearly indicates that methyl group directs the next coming electrophile to ortho or para positions only. Now let us consider the second example, that is nitration of nitrobenzene versus benzene. When benzene is subjected for nitration in the presence of concentrated nitric acid and sulfuric acid, nitrobenzene is obtained as product in 100% yield. So when the same reaction is performed for nitrobenzene, here nitrobenzene is a monosubstituted benzene. So from the mixture of nitric acid and sulfuric acid, there will be generation of nitronium ion in the first step. Now this nitronium ion can attack at 2 ortho positions, or it can attack at meta positions, or it can attack at para positions. So accordingly, there is possibility of formation of 3 isomers in this case also. This is the structure of ortho isomer where we have attached nitro group ortho to the first nitro group which is present on the benzene ring system, and this is the structure of meta isomer where both the nitro groups are meta to each other. So this is the structure of para isomer where the 2 nitro groups are present para to each other, that is exactly opposite to each other on the benzene ring system. When the resulting products were analyzed in this particular reaction, it was noticed that the reaction is favoring only formation of meta isomer in 100% yield. Okay, that means even though there is possibility for the formation of ortho para isomers, but yet the reaction is favored to give only meta isomer as the predominant product. This indicates that whenever group such as nitro is present, they will direct the next incoming electrophile to only meta position, but not at ortho or para positions. That means some groups are present on benzene ring system, they will direct to only ortho para attack, while some groups they will orient the next incoming electrophile to only meta position. Overall, in all these aromatic electrophilic substitution reactions of monosubstituted benzenes, we can notice that whatever the group that is already present on benzene ring system is very, very important. This is the principal group which will determine the orientation of next incoming group. Accordingly, there will be formation of different isomeric products. what type of product a reaction is going to yield, whether it is an orthoisomer, para-isomer or meta-isomer, will be decided by the group which is already present on the benzene ring system. Now let us consider case 2, reactivity of monosubstituted benzenes versus benzene. Now here also let us discuss two examples. The first example is sulfonation of benzene versus toluene. So when we perform sulfonation reaction, so here the reagent used is fuming sulfuric acid. Benzene upon sulfonation, we get benzene sulfonic acid in 100% yield. When toluene is subjected for same sulfonation reaction, there is formation of 62% of para-isomer, 32% of orthoisomer and 6% of meta-isomer as discussed earlier. Now if you consider time required to give the corresponding products, here benzene it takes only 20 to 30 minutes of time to give corresponding benzene sulfonic acid. Now on the other hand, the sulfonation of toluene, it takes only 1 to 2 minutes to give its corresponding products. That means toluene is taking less time to react when compared with benzene. The compound which takes less time to give corresponding product is highly reactive. That means among toluene and benzene, toluene is more reactive than benzene. Now what might be the reason for the high reactivity of toluene? If you see, it is always structural difference. Just compare the structures of toluene and benzene. Toluene consists of methyl group. Okay, so that means the high reactivity of toluene can be related to the methyl group. That means whenever methyl type of groups are present, they will activate the ring system towards the electrophilic substitution reaction. And thus, methyl group is considered to be an activating group. Now, the second example is nitration of benzene versus nitrobenzene. When we perform nitration for benzene, it gives nitrobenzene in 100% yield. Now, when the same nitration reaction is performed for nitrobenzene, there is formation of 100% corresponding meta-isomer as the product. Now, if you look at the rate of reactivity of these two reactions, benzene, it takes 40 to 50 minutes time to give corresponding nitrobenzene. While the same reaction is performed for nitrobenzene, it takes more than 1 hour to give corresponding meta-isomer. So based on this reaction time, we can easily make out that benzene is more reactive because benzene is taking lesser time when compared with nitrobenzene. So lesser the time taken to complete a reaction, greater will be the reactivity. So based on these two reactions, we can easily make out that benzene is more reactive than nitrobenzene. And what makes nitrobenzene less reactive when compared with benzene? So you can make out the structural difference between nitrobenzene and benzene. Here nitrobenzene is having nitro group. This nitro group present on the benzene ring system, making the ring system less reactive. That means it is deactivating the ring system, and that is the reason it is taking more time to complete the reaction. That means nitro group is a deactivating group. That means presence of certain groups, they will activate the ring system while the other groups will deactivate the ring system towards electrophilic substitution reaction. Based on these two case studies, that is orientation as well as reactivity in case of monosubstituted benzenes, the substituents are classified into activating groups and deactivating groups, ortho-para directors and meta-directors. Now let us look into these definitions. So activating group means any group that makes the ring more reactive than benzene is known as an activating group. Methyl group is an example for activating group. Deactivating group means any group that makes the ring less reactive than the benzene is known as deactivating group. Nitro group is an example for deactivating group. Groups can also be classified into ortho-para directors and meta-directors. So ortho-para directors means a group that causes the electrophilic attack chiefly at ortho or para position, then it is called an ortho-para director. For example, methyl group. Meta-director, a group that causes electrophilic attack chiefly at meta position to it is called a meta-director. Here nitro group is an example for meta-directors. So based on orientation of next incoming group onto the benzene ring system and also the rate of reactivity of monosubstituted benzenes, the substituents present on benzene are classified into activating groups and deactivating groups. Further, these groups were classified depending on orientation into ortho-para directors and meta-directors. Activating groups are mainly ortho-para directing groups. Hence, there will be only ortho-para director class. Ortho-para directors are classified into strongly activating groups, moderately activating groups, and weakly activating groups. So the examples under strongly activating groups are amines and hydroxyl groups. So here all the structures of primary, secondary and tertiary amines are given along with hydroxyl groups. Alkoxy groups. such as methoxy, ethoxy, and NHCOCH3 group, acetamido group. So these are the examples for moderately activating groups. Alkyl groups such as methyl and ethyl and phenyl group. These are the few examples for weakly activating groups. So all these are subclasses under activating groups. Now the other class is deactivating groups. Majority of the deactivating groups are meta-directors, but there are also a few ortho-para-directors present. So nitro group, cyano group, carboxylic group, ester, aldehyde, ketone, sulfonic acid moiety, and quaternary nitrogen. So all these are the examples for meta-directors. While halogens such as fluorine, chlorine, bromine, and iodine, these are considered as orthopara directors. So this is the classification of functional groups based on orientation and reactivity in monosubstituted benzene. So dear students, I hope this particular topic till now, it is crystal clear to you. So as I mentioned earlier, this table is very, very important. So you may get either 2 marks or 5 marks questions. I will show at the end of this particular live session based on this particular topic. So take a screenshot of this table. And also, meanwhile, you can keep your doubts. If you have any doubts or questions, you can keep in the chat so that I will answer them. Alternatively, if you are watching replay of this particular session at later stage, then a WhatsApp group link will be provided in the description. Okay, so you can join in that WhatsApp group and clarify your doubts. Okay, so keep posting your doubts. So meanwhile, I'll proceed for the next part of this particular session. So if you're a student who is attending this particular live session on the third day continuously, so that itself indicates your commitment towards your learnings and also towards your growth. Thank you so much for joining. So the group which is already present on the benzene ring system determines the next incoming group position and also the rate of reactivity of these monosubstituted benzenes. Now let us try to understand what is the theory behind the orientation and reactivity of aromatic electrophilic substitution reactions of monosubstituted benzenes. Here I have mentioned 2 examples under orientation, that is sulfonation of toluene and nitration of nitrobenzene. So when toluene is subjected for sulfonation in the presence of concentrated sulfuric acid, even though there is possibility for the formation of 3 isomeric disubstituted products, yet we have noticed predominant yields of corresponding orthoisomer and para-isomer. This clearly indicates that methyl group is an ortho-para directing group. Upon nitration of nitrobenzene in the presence of concentrated sulfuric acid and concentrated nitric acid, 100% yields of meta-isomer is observed, even though there is possibility for the other 2 isomers. So this clearly indicates that whenever nitro type of groups are present on the benzene ring system, they will direct the next incoming group to only meta position, but not to para or ortho positions. Now let us try to understand why certain groups allow for only ortho or para attacks, while other groups they will allow only for the meta attack. So this is considered as orientation of the reaction. Orientation is nothing but point of attack of the electrophile on the aromatic ring system. In order to understand the preferred point of attack of electrophile, we need to consider the rate determining step in these aromatic electrophilic substitution reactions. Now let us consider for benzene. The same step was explained in the previous course videos under general mechanism involved in aromatic electrophilic substitution. So for better clarity, you can refer to that video. So here 3 resonance structures of the resulting carbocation are drawn, and these 3 resonance structures are equivalent to the corresponding resonance hybrid. So from these 3 resonance structures, you can notice one common point. That is, in the first and third resonance structure, the positive charge is present at ortho positions. While in the second resonance structure, the positive charge is present at fourth position. That is the para position. So that means, so this positive charge is distributed even though around the ring system, it is strong at both ortho positions and para position. That means the effect of the group, whether the effect of group may be an activating or deactivating nature, this nature is strong at ortho and para positions. Let us consider if there is an activating group on the benzene ring system. It means when an activating group is present, it activates the ring system at all positions, but its effect is more prominent at ortho and para positions. We can observe the same thing in case of sulfonation of toluene. Hence, the activating groups such as methyl are ortho or para directors. Whenever a deactivating group is present on the benzene ring system, it deactivates the ring at all positions. But its deactivation is more prominent at ortho as well as para positions. That means its deactivation will be less at meta position. It is because of that reason, whenever deactivating groups such as nitro are present on benzene ring system, they direct the next incoming group to meta position. Hence, majority of the deactivating groups are meta directors. Now that we understood why activating groups are orthopara directors and deactivating groups are majorly meta directors, let us consider the same two examples. So toluene upon aromatic electrophilic substitution reaction, major yields of orthoisomer and para isomer are observed. It is because the resulting carbocations in ortho attack and para attack, they are highly stable. To understand this, let us consider the resonance structures of the resulting carbocation in each ortho attack, meta attack and para attack. Similar to the mechanism in the aromatic electrophilic substitution reactions of benzene, even the monosubstituted benzenes such as toluene, they results in the formation of resonance stabilized carbocation in the rate determining step. So, when electrophile attacks on toluene, the resulting carbocation structures are represented here. So, here these structures are drawn similar to the resonance structures how we have written for benzene. So, for better clarity, you can once visit that particular video. Similarly, when an electrophile attacks at meta position as well as para position on the toluene ring system, the resulting carbocation structures are shown here. So in each attack, you can notice the resulting carbocation has three resonance structures. So which attack is preferred in case of toluene? That depends on the resulting carbocation structure. So you can notice in these resonance structures of ortho attack as well as para attack. One of the resonance structure, that is which is marked here, you can notice the positive charge is present on the carbon bearing the electron donating methyl group. Due to the formation of carbocation, the ring carbons are already positively charged. Methyl group is an electron donating group, so it donates the electrons towards the positive charge, thus causing neutralization of the positive charge. As a result of which, the resulting carbocation in ortho attack as well as para attack is highly stable when compared with meta attack. So it is because of the formation of highly stable carbocations in ortho attack as well as para attack, toluene prefers substitution at ortho and para positions. Hence, methyl group is an ortho-para directing group. In case of aromatic electrophilic substitution reactions of nitrobenzene, major yields of meta-isomer is observed. This is because when electrophile attacks at meta position, the resulting carbocation is more stable when compared with the carbocations which are obtained in case of ortho attack as well as para attack. So formation of carbocation means it is the rate determining step. So now let us consider the rate determining step and the structures of resulting carbocations for the nitrobenzene in each ortho attack, meta attack and para attack. So these are the resulting resonance structures for nitrobenzene whenever electrophile attacks at ortho position. Similarly, for meta attack and also para attack also, we can write the structures. Again, these structures are written similar to that of resonance structures of aromatic electrophilic substitution reactions of benzene. So in each attack, you can notice here also, the resulting carbocation has three resonance structures. But here, the resulting carbocation stability is important. Out of the three resonance structures, in each ortho attack and para attack, one of the structure, that is the resonance structure which is highlighted here, you can notice the positive charge is present on carbon bearing the electron withdrawing nitro group. So here carbocation means already the ring carbons are electron deficient. Further, the nitro group is an electron withdrawing group. So further it causes withdrawal of electrons from this particular ring system. So this causes intensification of positive charge on the resulting carbocation. So whenever there is intensification of positive charge, the resulting carbocation is unstable. Okay, that means in ortho attack as well as in the para attack, the resulting carbocations formed are unstable. While this type of direct interaction of nitro group with positive charge is not noticed in case of meta attack. Whenever electrophile attacks at meta position, the resulting carbocation is more stable when compared with ortho and para attacks. Okay. That means whenever nitro type of groups are present, the next incoming electrophile prefers to attack at meta position only. It is because of this reason nitro group is considered as a meta-director. So here by this you might have understood the point of orientation. It mainly depends on the stability of the resulting carbocation. So in which of these attacks the resulting carbocation is highly stable, that particular attack is favored. Now let us try to understand the theory of reactivity in these aromatic electrophilic substitution reactions of monosubstituted benzenes. In the earlier course video, we have noticed that whenever sulfonation reaction is performed for both toluene and benzene, toluene is reacting faster than benzene. The reactivity of molecules is mainly because of the presence of certain groups. So the structural difference between toluene and benzene is that toluene is having methyl group. It means that methyl group acts as an activating group. And also from the other example, that is nitration of nitrobenzene versus benzene, we can easily make out that nitrobenzene reactivity is less when compared with benzene. So the structural difference between nitrobenzene and benzene, if you see, nitrobenzene is having nitro group. That means whenever nitro type of groups are present on the benzene ring system, they are making the ring system less reactive. That means they are deactivating the ring system towards the aromatic electrophilic substitution reaction. Thus, nitro group is considered as an example for deactivating group. Now let us try to understand how methyl group acts as an activating group while nitro group acts as a deactivating group through the theory of reactivity in case of monosubstituted benzenes. Again, to understand this particular concept, we have to consider the rate determining step, that is the carbocation formation in both these examples. So the first structure here, it represents the resonance hybrid structure of the monosubstituted benzene. Here G is an electron releasing group. Amino group, hydroxyl group, estamido group and methyl group. These are the examples for electron releasing groups. So when such type of aromatic compound containing electron releasing groups are subjected for aromatic electrophilic substitution reaction, it also generates corresponding carbocation in the rate determining step. So the same step is given here. So from the carbocation structure, you can easily make out that due to the presence of electron donating group, the electrons will be released towards the ring system. The ring, because it is carbocation, it is already bearing the positive charge. Now, electrons flow will be there from the electron releasing group towards the aromatic ring system. This causes dispersal or neutralization of the positive charge of the carbocation. Thus, it stabilizes the resulting carbocation. That means whenever electron releasing groups like amino group, hydroxyl group or methyl groups are present on the aromatic ring system, in the resulting carbocation structure, there will be dispersal of the positive charge. That means the formed carbocation is highly stable. As the resulting carbocation is highly stable, the ring will be activated towards these aromatic electrophilic substitution reactions. Let us consider an aromatic ring containing electron withdrawing group. So here G in the second case is an electron withdrawing group such as nitro, cyano, carboxyl group, aldehyde group, or it can be even a halogen. So whenever such type of aromatic compound containing electron withdrawing group is subjected for aromatic electrophilic substitution reaction, it also results in the formation of carbocation in its rate determining step. The same structure is shown here. From the structure of resulting carbocation, you can make out the ring carbons of this carbocation are already bearing the positive charge. But due to the presence of electron withdrawing group such as nitro group or cyano group, the remaining electrons, pi electrons, will be further withdrawn towards the electron withdrawing group. This causes further intensification of the positive charge on the ring system, due to which the resulting carbocation will be unstable. That means whenever electron withdrawing groups are present on the benzene ring system, the resulting carbocation is unstable. That means those groups, they cause deactivation of the ring system. So from this, we can easily make out that whenever electron releasing groups are present, they will activate the ring system. On the other hand, when the benzene ring system is having electron withdrawing group, they will deactivate the ring system. Now let us try to understand the same concept with a specific example. So the reactivity in aromatic electrophilic substitution reactions of monosubstituted benzene, it depends on the rate determining step, that is the formation of carbocation. So either for theory of reactivity or theory of orientation, we have to consider the rate determining step. So the respective carbocation in aromatic electrophilic substitution reactions of benzene, toluene and nitrobenzene, let us try to consider. So this is the carbocation structure in the aromatic electrophilic substitution reactions for benzene. And this is the carbocation structure for toluene. And this is the carbocation structure for the nitrobenzene. That means if you take three molecules, that is benzene, toluene, and nitrobenzene, when you perform aromatic electrophilic substitution reaction, any of the reaction, let us say nitration, sulfonation, any of these are electrophilic substitution reactions. These are the resulting carbocation structures. So from these resonance structures, we can easily make out their reactivity. So that is, whenever methyl group is present, because it is electron donating group, it donates the electrons towards the ring carbons, which are already holding the positive charge. Thus, there will be neutralization of the positive charge, causing dispersal of the charge, and thus it stabilizes the ring system. It is because of that reason, the carbocation which is formed in toluene is more stable. Hence, methyl group activates the ring system. While if you look at the carbocation structure in case of nitrobenzene, nitro group is an electron withdrawing group. So it will try to withdraw the electrons from the aromatic ring system. The aromatic ring carbons are already bearing the positive charge. Because of further withdrawal of electrons by the action of nitro group, the positive charge will be intensified on the aromatic ring. This destabilizes the ring system. Hence, the carbocation in case of nitrobenzene, it is unstable. Resulting carbocation in case of toluene is more stable, while the carbocation of nitrobenzene is less stable. Greater the stability of the resulting carbocation, faster the reaction. So once toluene gives its carbocation, within no time, the third deprotonation step occurs in the electrophilic substitution reaction, and it gives corresponding substituted product. Hence, toluene is more reactive than nitrobenzene. Okay, students, I'll stop today's class here. So if you have any doubts, you can share your doubts in the chat. You can type your doubts in the chat, and also please share your feedback in the chat. So I know this particular topic is little lengthy topic, students, but you can very briefly prepare for this particular topic. Most of the students will be afraid to answer this particular question, in fact, in the final examinations, and they will be feeling bored while explaining this also in the regular classes. But previously, whatever the explanation that I have given, exactly whatever the explanation that you find in the standard reference books, that is Marston Boyd, RIL, FINAR, okay? So similar type of pattern you will be noticing here also. But the overall concept, okay, no need to afraid by looking at the number of reactions or the way of the structures. But the whole concept you can summarize like this slide, okay? You will get this kind of representation nowhere, okay? Because none of the books, whatever you are referring, will be given there, given like this, okay? So what is the concept here is, when it comes to the we know about reactions of benzene. It will undergo aromatic electrophilic substitution reactions, and 5 model reactions I have discussed in the earlier live session. Okay. Now, when a group is present on the benzene, that is called a monosubstituted benzene. You can see the structure here. Model structure is given. Okay. So when an electrophile attacks on this type of monosubstituted benzenes, what type of products we can get? So as I mentioned earlier, or the product, meta product or para product may obtain. Okay, but there are differences. Okay, not all compounds are giving or the products are meta products. Okay, so how it is going to give, if in summary, if you see, whenever activating groups are present, okay, that is methyl, amino, hydroxyl, okay, phenyl group, all these are the activating groups. Okay, so we have noticed there predominant yields of orthoisomer and para isomer. Okay, here meta isomer will be formed in very, very negligible amount. Okay. Now, whenever this group which is sitting on the benzene, okay, structure, whenever this group which is already present on the benzene ring is a deactivating group, okay, then for such a compound, if electrophilic substitution reaction is attempted, then predominant yields of meta isomer is observed. Okay, so this meta isomer formation occurs only when the group which is already present on the benzene ring system is a deactivating group. Okay, again, there are different types of deactivating groups are there. Cyano is a deactivating group, nitro is a deactivating group, even carboxylic group is a deactivating group. Okay, as long as the deactivating groups belongs to any of this class, then they give meta isomer. Okay, but on the other hand, even halogen is also a deactivating group. Okay, but exception is observed when halogen is present. When halogen is present, even though it is a deactivating group, it gives ortho and para isomer only. It does not give meta isomer. Okay. So this is regarding the orientation. Orientation means when you perform an electrophilic substitution reaction for a monosubstituted benzene, what is the point of attack of the next incoming electrophile, where this Y group will be attacking on the benzene ring system. Okay, so that is what we discuss generally under orientation. Now, for that to explain that only, several examples were given in the textbooks, or the same examples I discussed in the earlier session also. Okay, that is sulfonation of toluene, okay, nitration of nitrobenzene, comparing with the reactions of benzene. All these examples were taken, okay, to explain the theory of orientation. Okay, now coming to the reactivity of the molecules, all molecules, okay, that means when the molecule is having nitro group, cyano group, or methyl group, all these monosubstituted benzenes, they do not take same time to complete the reaction or to give the corresponding product. Okay, so if you see in case of activating group, whenever activating groups or electron releasing groups are present, they will take less time because they are the activating group. They will activate the ring system towards the electrophilic substitution reaction. So the reaction occurs very fastly. Okay, so they take less time. That means these are the more reactive compounds or reactive groups. Okay, on the other hand, whenever deactivating groups, which I mentioned earlier, cyano, nitro, carboxylic group or halogen groups are present, they will take more time to complete the reaction. It is because they are less reactive. Okay, so this is taking more reaction. The compounds which take more reactive time, the compounds which take more reaction time means they are less reactive towards the reaction. Okay, so in that way, this particular part of the discussion, it is related to the theory of reactivity. How much of time these monosubstituted benzenes take to give corresponding product or to undergo electrophilic substitution reaction. Okay, so this was explained by again referring to the reactions of benzene with toluene, where toluene is taking a very small amount of, very minute amount of time, that is just 1 to 2 minutes it is taking, and it is undergoing the electrophilic substitution reaction. It is because methyl group is an activating group. Okay, that is what is discussed under theory of reactivity. When it comes to deactivating group, nitrobenzene was considered as an example. Nitro is a deactivating group, so it will take more time, hence it is less reactive. Okay, so the reactions of nitrobenzene are discussed in the earlier discussion. Okay, so this is the overall concept. You can take print screen of this particular slide. I'll remove all the annotations. Okay, so you can take screenshot of this particular slide. So if you understand this particular slide or schematic representation, based on this you can write all the earlier discussion whatever I explained previously. Okay, because majority of the textbooks, they start with that discussion. That's why I explained in that way, but many of the students, they will get confusion. Okay, but overall concept you can understand in this way. Okay, so the group which is present on the benzene ring system is important. Now this group can be an activating group or a deactivating group. Whenever activating group is present, reaction is faster. That means they are more reactive. Within less time they will give the product. Okay, and they give ortho-para isomers. Okay, on the other hand, whenever deactivating groups are present, okay, they will take, because they are deactivating the ring system towards the electrophilic substitution reaction will be delayed. That means they will take more time because they are less reactive. Okay, now again under deactivating group, all the groups such as cyano, nitro, carboxylic groups are meta directors. They will give only meta product. But when it comes to halogen, little difference will be there, exception will be there. So it will give only ortho-para isomer. Okay, when it comes to the reactivity, it is similar, but it gives ortho-para isomer. So if you understand this particular slide properly, based on this, you can write all the earlier discussion. If this particular slide and its explanation is clear to you, better you start answering from this particular slide, and whatever the examples that you can able to remember from the earlier discussion, you can add. So in short, in that way also you can prepare for this particular topic. It is because this is a definite question, my dear students. Okay, you can take print screen of this particular slide. So let us see a few important model questions from this particular topic. So you can see these are some model questions. What are ortho-para directors? What are meta directors? Or define ortho-para and meta directing groups with examples. All these are 2 marks questions. Why amino group is a activating and ortho-para directing group? And why nitro group is a deactivating meta directing group? Explain. That is what we discussed in the previous discussion. Okay. So that means this is referring to the orientation. Okay, that means this question is related to the orientation. Okay. Now the next one is classify substances based on their effect. Electrophilic substitution reactions of monosubstituted benzene. Okay, that means again you will give that particular table. Okay, and discuss about activating and deactivating groups with examples. 2 marks. Okay, that means if you just remember this particular table, that is more than enough. Okay, the definitions whatever I have explained previously. In a single slide, I explained activating group, deactivating group, or the para-directors and meta-directors definitions, and this table. Okay, so this is very, very important. If you have not taken print screen of it earlier, you can take here. This is very, very important, students. Okay, so all the 2 marks questions, maximum they will come based on this table only. Okay, just you need to include the definition which I have given in the previous discussion. Okay, so I hope you have taken print screen of this particular slide. If not, you can take, I'll give little time. Okay, sometimes they may ask only to write about ortho para directors. Okay, sometimes they may ask to write about meta directors. Okay, or what are activating groups? Give examples. So in that case also you will give this particular category of the compounds. Okay, now coming to the 5 marks or 10 marks questions, these are the questions. Okay, so that is covering the overall topic. Okay, these questions covers overall topic. So that is theory of reactivity and orientation in monosubstituted benzene. That means whole you have to write, or you write the schematic diagram which I have shown earlier. Let me show again. So you write this, from this try to give some examples. So here you can give reactions of toluene as an example. When it comes to deactivating group, here you can give examples of nitrobenzene. Wherever nitrobenzene reactions I have explained in the previous discussion, you can write about that. Okay, so like this also you can mention. Now the next question. So explain the effect of electron withdrawing groups on reactivity and more orientation of monosubstituted benzene. Electron withdrawing group means there we have discussed reactions of 2 model compounds. One is toluene, another one is nitrobenzene. Okay, so toluene is an example for electron donating group. Okay, that means methyl group of the toluene. Okay, is an example for electron withdrawing, electron donating group. And here withdrawing group means it is nitro group. Okay, so nitrobenzene reactions you can consider whatever the explanation that we have discussed for nitrobenzene reactions, that part only you will write here. Okay, explain the orientation reactivity of chlorobenzene, okay, of further electrophilic substitution reaction. So you will take, we have discussed for toluene and nitrobenzene. So here they have asked for chlorobenzene. Okay, so chlorobenzene reactivity is less, but when it comes to, even though chlorine is a deactivating group, as I discussed in that schematic diagram, okay, chloro group is an ortho-para director. Okay, so you will write the products. You will take as an example either sulfonation, nitration of chlorobenzene. But when it comes to the products, you will be giving orthoisomer and para-isomer structures only, because chlorine is a ortho-para directing group. Okay, and explain the deactivating nature of chlorobenzene is also asked. Okay, these are interrelated questions. So here they have asked logically. Okay, and this is a straight question. That is the difference between these two questions. Otherwise, it refers to the same topic. Write about electrophilic substitution reactions of monosubstituted benzenes. So here, that means you will take either toluene, nitrobenzene or chlorobenzene as an example for monosubstituted benzene. Then you give the reactions like sulfonation of toluene is already explained. Nitration of nitrobenzene is already explained under theory of orientation and reactivity. So the same examples you will take and explain as the reaction. Okay, so that was the small difference. So same thing you can do here, and explain the nitration reaction of aniline with mechanism. Okay, so this is nitration of benzene, you know. So what is the mechanism in the nitration of benzene? 3 steps are there. So similar to the nitration mechanism, you will write the nitration mechanism for the aniline. Okay, so there in the nitration of benzene, you have written the nitration mechanism for the benzene. Here for aniline, you will write the nitration mechanism. Okay, that is the only difference. But when it comes to the product, because aniline consists of amino group, and amino group is an activating group and it is a ortho-para director. Okay, so here you will give orthoisomer and para-isomer structure as the product. Okay, when it comes to the orientation. Okay, so that is how you have to give. For aniline, you have to write as ortho nitro aniline, para nitro aniline. You will write them as products. That is the only difference. Okay, so these are some of the questions, students. As you have seen, this particular topic is very, very important. And not only for your university examination, if you are a student who is attempting for GPAT, okay, also this topic is very, very important, students, because here I have given very few model questions. In fact, in every year GPAT, one question is coming from this particular topic. So you can see here, this is a direct question given in GPAT 2023. Following groups exert any one of the effects on electrophilic aromatic substitution. Identify whether all 3R belongs to which class. Okay, so here methoxy, ethoxy and estamido groups are given. Okay, whether they are weakly activating, deactivating or moderately activating or strongly activating, we have to mention. Okay, so based on that table, So I will show the table once again here. So you can see methoxy, ethoxy, estamide, all they belongs to moderately activating group. Okay, so the same answer was highlighted here. Okay, so this is one of the GPAT 2023. And again, in the same paper, another set, you can see this question. So the correct rank order of orientation of sulfonation in toluene is, okay, 4 options are given. What is this question? It is being asked about the reactions of toluene, sulfonation of toluene, the first reaction which I discussed under orientation in the previous discussion. Okay, so there, in case of sulfonation of toluene, we have noticed predominant yields of orthoisomer and para-isomer when compared with meta-isomer. So there I discussed whether I discussed or in the textbooks also, the representation was given in the form of ortho, para, meta-isomers. Now in the question, GPAT 2023 question, they give number. That is the only difference. Benzene ring has been given numbering, and with respect to number, the names of the products were given here. Okay. So this 4-methyl benzene sulfonic acid is nothing but the para-isomer. 2-methyl benzene sulfonic acid is nothing but the orthoisomer, and 3-methyl benzene sulfonic acid is nothing but the meta-isomer. Okay, so in case of toluene reaction, because methyl group is an ortho-para directing group, we get ortho-para products predominant. So the first option is the correct option. Okay, so in that way, a small tweak has been made in the question. Okay, otherwise it is also one-way direct question. Now the another question from GPAT 2024 paper is, which of the following is easily nitrated using a mixture of nitric acid and sulfuric acid? Which of the compound undergo nitration easily? This is what the question means, whether it is toluene, nitrobenzene, chlorobenzene or fluorobenzene. Okay. Fluorobenzene consists of fluorine, chlorobenzene consists of chlorine, nitrobenzene consists of nitro group, while toluene consists of methyl group sitting on benzene structure, right? Okay. So now the group effect you have to see. Okay. Out of these groups, which group is an activating group? Just now in that particular table I have shown, methyl group is an activating group. Okay. When activating group is present, that particular compound easily undergoes electrophilic substitution reaction. So here the correct option is toluene. Toluene can easily undergo electrophilic substitution reactions rather than nitrobenzene, chlorobenzene or fluorobenzene. Okay. The detailed explanation for the answers of these 3 questions were in fact discussed in one of my earlier YouTube video. I'll be giving the link for that particular YouTube video also in the description, so that you can refer to that particular video if you are planning for GPAT or NIPER type of the competitive examinations. So with this, we have completed unit 1, students. This is the 3rd day of this particular course. No, so each unit I'll be covering for about 3 days, I told. So this is the 3rd day, and by this we have completed the unit 1. So because we have completed the unit 1, let us quickly summarize the few important points what I discussed in these 3-day sessions. Okay. That is, benzene is aromatic hydrocarbon, as you are aware, and the molecular formula of benzene is C6H6, and it occurs as colorless liquid. The carbon atoms of benzene are in sp2 hybridization state. That is what I discussed under orbital structure of benzene. And in the valence bond theory and also in the resonance structures, I mentioned that all the carbon-carbon bonds which are present in benzene are having double bond character. This is also one of the important things. Okay. And how many structures are possible for, how many resonance structures are possible for benzene? As we have seen, 2 resonance structures are possible, which are proposed by the Kekulé. And the resonance energy of benzene is 36 kilocalories per mole. Okay. Now the benzene is stable. Why? What is the reason we call benzene as stable molecule? Due to resonance. And further it is evidenced with the help of the less heats of hydrogenation when it comes to benzene. Now coming to the typical reactions, as I discussed in earlier class, that is yesterday's class, aromatic electrophilic substitution reactions they will undergo. And the rate determining step in this particular reaction is the formation of resonance stabilized carbocation. That means it is the step 2 in the reaction mechanism formation. Okay. Now coming to the key important points in today's discussion, monosubstituted benzenes also undergo reactions similar to benzene. Okay, that means they will also, toluene, nitrobenzene, chlorobenzene, they will also undergo electrophilic substitution reactions similar to benzene. Okay, the group that already present on the ring determines the position of the next incoming electrophile. This is what repeatedly I discussed in today's session. That is what is known as orientation. Okay, whether the next incoming group whether the next incoming group position itself to ortho position, para position or meta position. Okay, that is decided by the group which is already present on the benzene ring system. Accordingly, ortho, para and meta directors were given. Okay, So the substance that stabilizes the ring will activate the ring system towards the electrophilic substitution reaction. This is what we have noticed under the reactivity of toluene over the nitrobenzene. Okay, so these 2 points are related to the reactivity. The substance that destabilizes the ring will deactivate the ring system. Because they are destabilizing the ring system, they will destabilize the ring system towards the electrophilic substitution reaction. Okay, and groups like nitro or electron withdrawing group, and they will deactivate the ring system. So accordingly, we have discussed also about the activating and deactivating group. Okay, so this is the overall summary of Unit 1, students. By this, we have completed Unit 1. So related to overall Unit 1 topics, if you have any doubts, you can share in the chat. Alternatively, you can post your doubts even in the WhatsApp group also. So thank you so much for successfully attending the third day live session also, students. So time to revise all these concepts. Very soon quiz will be enabled. So remember, students, Unit 1 topics are very, very important because majority of the questions you will get from Unit 1. So overall, if you see, mastering benzene is the first step in your success journey. So if you master benzene means without any fear, you can attend your final examinations and you can score marks well. If this session is useful to you and if it added value to your learnings, please subscribe my channel, and also please share my channel link to your friends also, so that they will also benefit from these concepts. And please share your doubts and your valuable feedback in the comments. And from tomorrow onwards, 3 consecutive days, I will be covering Unit 2 important topics. Thursday, I'll be covering chemistry of phenols, and Friday, I'll be covering chemistry of aromatic carboxylic acids, and Saturday, I'll be explaining about aromatic amines. So by that, second unit will be completed. Okay, that means by this Saturday, second unit will be completed. So Sunday also, class will be there 6 to 7. So Sunday, I'll be starting Unit 3. I know, students, this is year-end day, that is 31st December. It is very hectic for you to follow this particular session. So thank you so much for joining in spite of your busy schedule. You sacrificed your 45 minutes for this particular live session. Thank you so much. And tomorrow, even though it is New Year, again, class will be there from 6 o'clock. Okay, so don't skip the class. Okay, if it is New Year means you have to take new resolutions. Okay, and whatever you have not achieved in this year, make a list of that, and also make a list of the things whatever you want to achieve in the next year. Okay, that means what are your New Year resolutions. Okay, after completing this particular class, take 1 hour time, review your 2025 performance, and make solid resolutions. Okay, for 2026. Write on a paper. Okay, write on a paper and let me know in tomorrow's live session. Thank you so much for joining in, and take care. I'll meet you in my next session. So in these two course videos, that is effect of substituents on aromatic electrophilic substitution reactions of monosubstituted benzene and the theory of orientation and reactivity in the aromatic electrophilic substitution reactions of monosubstituted benzenes. So these two course videos mainly consist of